Today we're going to be looking at matrices, specifically an introduction to what a matrix is and matrix addition and scalar multiplication. We'll be doing them both by hand and with a calculator, and we'll be finding some difference in scalar multiples of matrices. Before we can get into any operations on matrices, we want to define what a matrix is first. Matrices is just plural of matrix as well, in case you were wondering. So a matrix is an array of numbers written within a set of brackets. They're square type of brackets and arranged in a pattern of rows and columns. So here I have what's called a 2 by 3 matrix. I'm calling it A, and it says the first row is 2, 3, 5, and the second row is 6, 5, 2. So you can see here's that first row, and there's the second row. You can also describe the columns and things like that. This particular matrix has what's called 6 elements in it. Those are the different entries. Okay. It has 3 columns, 1, 2, 3, and 1, 2 rows. So that's where this 2 by 3 is coming. It's the dimensions of a matrix with m rows and n columns is m by n. So the elementaries entries, those are the numbers in our matrix. Nope. Numbers in our matrix. So let's look at this within a context. A local bakery keeps track of their sales. Now organize the data given into 2 matrices. So apparently it has 2 different shops, one in New Canaan and one in Greenwich. And for February, they sold 650 rolls in New Canaan and 540 in Greenwich. See how I'm setting them up? This is going to organize my data. So the first column is all of my rolls information. The first row is going to be New Canaan. I'm just going to put the labels on the outside. And the bottom row is Greenwich. Then for cakes, sorry. Important distinction there. 220 cakes in New Canaan and 200 cakes in Greenwich. And then 32 pies. Apparently their pies are not a big seller. And 30 pies here. So see how my February, this first row is all of my numbers from New Canaan. And the second row is all my numbers from Greenwich. And I've organized them. So it's really important that matrices keep things organized. So we don't want to switch the cakes and the pies around because that wouldn't give us valid information when I go to work with it in another scenario. So when I write my March one, I'm going to keep New Canaan on the top row, and I'm going to keep Greenwich on the bottom row, and I'm going to keep it as rolls first, cakes second, and pies third. And I'm doing that, I'm keeping it consistent so that when I go to work with them, if I'm going to do any combining with them or anything like that, we'll be able to have meaningful data. Okay. So now I did set these both up as 2 by 3 matrices. There was nothing stopping me when I set this up to make them 3 by 2 because there's no information in the question saying you must have a matrix that's 2 by 3. So I could also model this same problem set up like this: 650, 220, 32, 540, 200, and 30. Okay, this would give me the same information. It's just modeled in a different setup. Okay, I happen to do it a wider one, basically because I just sort of thought about it as this. That was my matrix right there, and I just put it in that format. So the first operation we can do is called a transpose of a matrix. It's basically interchanging the rows and columns, and it's denoted by A of t. So if my A is this 2, 3, 5, 6, 5, 2, you can see A of t, how this row that was 2, 3, 5 has now become this column 2, 3, 5. And this row of 652 has become this column of 652. Very similar to how I just mentioned, we could have modeled it a different way. Okay, but it is called a mathematical operation. So find f of t. Oh, look at that. I already did. And maybe I'll be able to copy and paste. It's only a maybe. Well, that was not that effective. So f of t, 650, 20, 32, and 540, 200. Transpose is an important thing, but in terms, it's important for manipulation to get things to work together if they don't already work well together. All right, pause the video and find the transpose of this matrix B. All right, so B transposed means this row of 5, 2, 6 is going to go 5, 2, 6. See how that's becoming my column? This row of 1, negative 5, 3 is going 1, negative 5, 3. And last but not least, this 408 is going to go 408. Ta-da! Transpose. Easy as pie. So, I just told you we're going to look at it with the calculator. So whenever I want to put a matrix, I'm sorry, I'm deciding where I want to put the calculator. When I want to put a matrix in our calculator, we're going to have to go to the matrix menu. The matrix menu is second, and then x to the negative 1. And you can see in blue it says matrix. When you do that, it gives you this screen right here. Okay, and it just gives you a bunch of different spots where we can type in matrices. And for example, I'm going to take this matrix B and put it in as, I'm going to call it, well, why not call it B? Now, if I do B right now, it's going to just give me an error because I haven't put anything into it. So we'll do second matrix, and we'll go over to edit. See that over here, edit? Okay, so I'm going to edit B, and you can edit any of them at all. It doesn't matter which one you go to edit. Then the first thing it asks is, you can see it's a 1 by 1 right now. I need to change the dimensions. This B happens to be 3 rows by 3 columns. So I'm going to change the dimensions to be that, 3 by 3. The moment you type in the 3s, you can see that the dimensions got bigger. Now I'm going to type in my numbers. It's very important if you're going to type in, you're going to use the calculator for any of these, you have to type in very carefully. One small sign error or typed in number wrong, and all of your calculations will be wrong, and it will be very hard to determine your mistake. Okay. So I typed in those. I've got, oh, come on, there we go. I'll give it 2. Double check 5, 2, 6, and sometimes when I double check, I actually go a different direction. So 8, 0, 4, 8, 0, 4. 3, negative 5, 1, 3, negative 5, 1, 6, 2, 5, 6, 2, 5. And the reason I read it backwards, or sometimes I'll go up and down the columns instead, is the same reason why if I'm checking for spelling, I read the sentence backwards, so that my brain doesn't autocorrect it to be what it's supposed to be. And I can find mistakes better that way. So now if I go and ask it for matrix B, and hit enter on it, it gives me that matrix. And yours might have one set of big brackets if you have a newer calculator. That's cool too. Now, why would we spend all this time? Because I can do things with this. So matrix B, I enter that. And what have we learned? We've learned how to transpose. So let's go over to math, that middle column. You see this little t? That's going to transpose it and flips it over, and we get the same thing we got there. How cool is that? So, all right, next thing we want to talk about is scalar multiplication, which is basically multiplying a matrix by a real number C. So basically what you'll do is multiply each entry in the matrix. So if I have this matrix 5, 0, 2, 3, negative 6, 5, when I want to find 4D, I'm going to take 4 and multiply it by all of the pieces. It's kind of like distributing it 20, 0, 8, 12, negative 24, and then 20 again. Done. Okay, I'm just going to work with this B for a moment. If I wanted to multiply it by, say, 3 times that B, and that gives me 3 times, and if I look at what that B was, 3 times it, 15, 6, 18, 3, negative 15, 9, 12, 0, 24. Scalar multiplication, depending on how much you're doing, what numbers you're multiplying by, most of the time I just multiply it out by hand, but you can use the calculator as well. Suppose that you know that the bakery always does 50% more business in April than March. Find a matrix to describe April sales. So I'm going to write out March again for us. I'm going with the wider one that I had before. 840, 250, 50, 800, 250, 42. All right. So that's what March is. If they're doing 50% more business, that means I'm going to multiply by 1.5. Okay, 1 to keep it the same, and then the 50% increases the 0.5. So April is going to equal 1.5 of March, which is, now I'm going to multiply each entry by 1.5. So 1260 rules, 375 weeks. I don't know why I'm typing this in because I know it's 75. That's cool. 1200, 5, and 63. So that would be describing April. And so take a moment, pause the video, and try all these examples. Did you try them? All right, so for my scalar multiplications, I'm going to have 20, 15, negative 25, and on this last one, notice I have variables in there, but it's fine. I'm just going to have variables in my answer. So 4c times 0 is 0, 4c times 6 is 24c, 4c times 0 is still 0, 4c times 3a is 12a. That's it. So we can do matrix addition, that's adding the corresponding elements into matrices of the same dimension. It's really important here. Critical piece here is the same dimensions. You can only add two matrices if they have the same dimensions. And I'm also going to go back to our example for a minute. And they have to, those dimensions have to make sense. So I'm going to add rows and rows. We don't want to be adding rows and pies because it's not going to give us the same information. Okay, and it makes sense because if in March I introduced cream puffs, I'd have another column here and I would not be able to add them together unless I added a column here for cream puffs and placed zeros in them. That's how you can adjust for adding inventory to a bakery kind of thing. So Let's see, we're going to add here. So again, always check first that the dimensions are the same. And if the dimensions are not the same, you would say the sum is undefined. So my dimensions are the same, boom, because I have a 3 by 2 and a 3 by 2, therefore I can add them. So 3 plus 0 is 3, 6, and negative 1 is 5, 5, negative 3, negative 3, and 2. Ta-da! All right, so we are going to take our February matrix and our March matrix together, add them together to find the total sales over the 2-month period. I'm actually going to do that with the calculator. Okay, so where are those? There's February and there's March. So I'm going to go back to my matrix window, which again is second x to the negative 1. I'm going to go over to edit, and I need to make these 2 by 3 matrices. They are 2 rows and 3 columns. If you happen to put the dimensions in wrong, you would see that it was the wrong shape and just split up your numbers. 650, 220, and 32, 540, 200, and 30. So there's my first one. I put February in A because I didn't want to scroll all the way down to F. And I'm going to put March, going to go into the B spot. So here I want to change it to be a 2 by 3. And see that got rid of that extra row for me. March we had 840, 250, 50, 800, 250, 42. All right. So, too far. So here was my piece. One thing to note right here, you can see this label on the bottom where it says 2, 3. That's saying second row, third column. And it's describing that entry. So I have that. And I have this one. I have this one. So here's an A, what I put in A and what I put in B. And now I just want to add them. Ready? So I'm going to go second matrix. I'm going to take A, add, oh no, this is revolutionary, B. That's how I have it typed in, and then it adds them together for me. How fantastic. So and what this is telling me, so the answer here, I'll write it out for us. 1490 or 782. Notice the result has the same dimensions as the matching dimensions. So what this is telling me is New Canaan sold 1,490 rolls, 470 cakes, and 82 pies in that 2-month period. And Greenwich sold 1,340 rolls, 450 cakes, and 72 pies in that 2-month period. Okay. So take a minute and try these examples. You tried them, right? Okay. So I'm going to add here 4 and negative 2 is 2. And 4. I'm going to add here, oh, I have some variables. So negative 4n plus 4, I have no like terms, so I'm just going to leave the expression. N plus m minus 5, n plus m minus 5, negative 2n plus 3m. See, you're all intimidated by this one, but it really wasn't much at all because there's no like terms. I'm going to add these. So notice this one matches as well. I have another 2 by 1 and 2. And ooh, here, little tricky. I have a subtraction. I bet you did it instinctively though. We're just going to subtract our values instead. So negative 5 minus 6, negative 11. 2 minus negative 5 is 7. Negative 2 minus negative 6. So the two negatives become a positive there, and so that'll be 4. 4 minus 1 is 3. Negative 2 minus 3 is negative 5. 0 minus negative 3 is 3. Okay? So again, you probably did it instinctively, but matrix subtraction is subtracting the corresponding elements in two matrices of the same dimensions. You can also do more than one operation. You want to do the scalar multiplication first, though. And that makes sense. Goes back to PEMDAS. So here, here I've got 1, 1, 6, 4, 0, 0, plus negative 20, 30, 5, 5, 20. And now I'm going to add them 1 and negative 20, 19, 1 and 31, 11, 1 and 20. Boom. Here's the same question written in a different format. Given A and B, find 2A minus B. So it's really saying do the scalar multiplication on A. So 2 times A minus B. 2 minus 7 is negative 5. 9, 4, 5, 18. I didn't have any examples in here, but I'm just going to do one over to the side for a minute, just so you can see. So notice here I have a 2 by 2 and a 2 by 3. My dimensions don't match, so all I would write is sum on the right. Okay? And your calculator would give you an error message too if you tried to add things that didn't have the same dimensions. One last thing, when two matrices are equal, so notice here I have an equal sign between them, then all of their corresponding elements are equal. That's telling me that this piece and this piece have to be equal. I'm going to add that corresponding. This one and this one are going to be equal. Well, yeah, it says 5 and 5. Good job. Little checks on it. 6 and 2C and A 7. So what I can do now, if I know these have to be equal, then B plus 2 has to equal 3. So B is 1. I also know 6 has to equal 2C. So 3. And then last but not least, A is 7. So boom, that one's done. Okay. And so what we've done today is we have defined what a matrix is. We've set them equal to each other and to find variables. We've added them, subtracted them, and done scalar multiplications. So this concludes our introduction to matrices.